gives me enormous pleasure to introduce, Professor Sir Andre Geim, who really needs no introduction, but I will say a few words. He's the Regius Professor at Manchester. He got the 2010 Nobel Prize in Physics for his groundbreaking research on graphene. He's a member of so many learned societies, I won't go on about them. He has many, many highly cited papers. And notably, he was awarded the 2000 Ig Nobel Prize as well. So that's very interesting to get both the Nobel and the Ig Nobel Prize. So, without further ado, please come up to the stage, Andre.
Good afternoon. Last year, people make a complaint to Tony Cheaton, our chairman, that many talks by invited speakers about the work which has been done sometime 70 years ago, and they want a cutting-edge research. So on behalf of our community of elders, not mentioning anyone in particular, Michael and Tony, I took an offense, so I decided to try to give a talk on the cutting edge. This is a talk I have given first time 3-4 months ago, and at a couple of conferences, and it's about our recent work. It's about quantum condensed matter physics, about electronic properties of graphene. I'm not that evil, so I would not go through transparencies as I normally do at those conferences. I'll show exactly the same transparencies, but try to explain physics behind rather than just showing the curves. So here we go. So somewhere about nearly 20 years ago, in 2008, I declared in one of reviews that graphene is dead because we know everything about electronic structure and so on. And indeed, so many people, tens of thousands of publications about electronic properties of graphene, and its spectrum is quite well known. It mimics electronic spectrum of relativistic particles moving with the speed of light. It's a conical spectrum, so so-called massless particles. So, and why we thought that everything is done, the most interesting point of graphene is here, when you approach to very low energies. Unfortunately, it's hard to approach. Initially, the first 10 years or 5 years, people mostly, including ourselves, investigated rather inhomogeneous structure, and here you see puddles of holes and puddles of electrons, so only here it's somewhere on those boundaries you approach the neutrality point, low energies. As the time progressed, people learned how to make graphene more and more pure, but still there were puddles left. Quality of graphene is usually described in units of this kind of weird units, and already for 10 years, the mobility is more than 1 million, and you see how you go from holes to electrons applying gate voltage, and you see sharp peak, which is approaching neutrality point. Still, you only approach the best samples so far. You get those electron-hole puddles, and per square micron, you get about here several 10 to the 9. It means hundreds and hundreds of electrons and holes when you are at this peak and so on. And nothing seems to be could be done, and there are two ways to investigate what's going on. One of those ways, which surprisingly not many people tried, is to increase temperature. This is a regime of inhomogeneous one, but when you increase temperature, you excite electrons and holes, and eventually you can ignore those puddles and so on. Recently, we found another way. It's so-called proximity gate. You have to put a metal plate. In our case, it's a thin crystal of graphite, which is at 1 nanometer distance from graphene, and there is a screening. You really have to put it very close because unfortunately there is a parameter about 10 which allows you to screen inhomogeneity at of spatial size about 10 times larger than the distance to the gate. So when you get this one, proximity gate, which is a recent technology, this is what we got just 1-2 years ago. That was the state art. Mobilities are millions, tens of millions, and that's how you evolved. This peak becomes extremely sharp, 100 times sharper than before. So essentially, per device area, you have very few extrinsic charges. So the system becomes quite homogeneous. So you can approach this neutrality point or Dirac point within 1 milli-electron volt, which gives you access to additional physics. And that was previously in homogeneity. And you see the number of excited carriers in this case is just follows the theoretical dependence, and only at low temperatures you get some signs of inhomogeneity playing out. So that's our system, and we got previous champion was gallium aluminum arsenide heterostructures, which is very popular system to study all quantum condensed matter physics, and we beat this system in terms of mobility. So how do we know that the mobility is really high? Shumnikov-de-Grasse oscillations, essentially Landau quantization, starts at fields nearly as low as Earth's magnetic field. You start seeing very pronounced quantization effects, which allows you really say that it's extremely high quality system, at least 10 times higher than any other system before. Then you can a little bit increase magnetic field, and you see quantum Hall effect, which usually requires large magnetic field available in superconducting magnets. In this case, you apply rather small magnetic field of about 5 millitesla, and you see perfectly developed quantum Hall effect. So that's a good system, and we hope that a lot of new results will come out of this one. And it's the development which came about a year ago or even less. So most of rest of my talk will be about how to overcome this inhomogeneity, not by the gate, proximity gate in close proximity, but just increasing temperature, moving from this inhomogeneous regime to a regime where temperature excites electrons and holes, and you can forget about this inhomogeneity. So it's just the highest quality samples which were available 2-3 years ago, and we study those ones. what about new physics? It comes immediately when you look at how the resistivity at this near the neutrality point behaves as a function of temperature. That's inhomogeneous regime, which we want to avoid, where people just, as we as well, ignore this regime. So, but when we go to this electron-hole plasma regime, you figure out that it's just constant resistance. And it's a very simple system. You can characterize this system. What you immediately find out that scattering time, which describes this resistivity, is given by Planckian time. It's uncertainty principle. This energy of our excited electron hole, this Planck constant, this is so-called Planckian time. So what we get from the plasma, our system at the neutrality point, not just a metal, it's so-called strange metal. Some in the audience maybe heard about strange metal, and their feature is that resistance is proportional to the temperature linearly. In our case, it goes to the constant, but the difference is quite simple. In case of normal strange metals, the number of the carriers remains constant. In our case, the number of the carriers increases with temperature, which compensate this dependence here. So the conclusion from just one of these observations that we get at the neutrality point, moving so close to this cross-section between electrons and holes, we get a high electronic quality system with simple spectrum, and we can study the same physics which people puzzled about in strange metals, where there are so many uncertainties how to treat it. So let's study this strange metal consisting of electrons and holes, and this is again this kind of the curves, longitudinal resistivity or resistance here, and hole resistance, and thousand people measured this behavior before over the last 20 years, including many curves like this published before. So, but now the difference is that we use a small magnetic field, and the most important difference, we do this not at low temperatures, but at room temperature. At low temperatures, this regime was ignored. Inhomogeneous regime, forget about this. In our case, we can't forget about this because we know that we have well-defined electron-hole plasma, so it's well-defined system, so we try to interpret what these curves mean, and we immediately find out that using simple approximations, which usually people use outside this regime somewhere here, do not apply for this regime of plasma, of excited electron and holes. So what do? We use a little bit more analysis, theoretical analysis, in which we take into account that there is not only, say, phonons or other scatterings in the system, but that electrons and holes, they can kick each other. We take into account interaction. With this kind of analysis, we get 2 times here, and also it's rather involving analysis. To prove all this one, we can explain both curves, and from 2 curves and 2 unknowns, we get 2 times. So it's curves, it's a boring curve, it's just scattering times as a function of density, so I don't want to focus your attention on this one. But what is interesting in terms of physics, we can get so-called mobility of electrons and holes. Mobility is just the speed of electrons and holes divided by electric field applied. So I take one of those curves and at room temperature and start looking in more detail. That's analysis where we and other people have done before, simplistic calculation. This is where it's all correct. Here's the divergence because of this double carrier system, which was not done before. So what we see here that at a finite concentration regime studied before, it's a phonon-limited regime. At phonons just scatter electrons and hole, nothing special. Then we go here at the neutrality point, we go to Planckian electron-hole scattering and get the same result which I described before. What is interesting that as we go from electrons to holes, for example, and holes start dominated, negative means holes are majority carriers, electrons essentially become negative mobility. Essentially, they move in the opposite direction to apply electric field, which seems to be impossible. You apply electric field in this direction and your carriers move in the opposite direction. In fact, this is quite easily understandable in terms of physics, where it comes from. So you have electrons moving in this direction, holes try to move in the opposite direction, but electrons drag them, scatter them so frequently that they force holes move in the opposite direction. That's where negative mobility comes from. So that's one effect. Now we continue investigating this system and put it in relatively small magnetic field. And this is interesting because we get compensated at this neutrality point. We have a compensated metal, which means number of electrons and holes at this point at finite temperatures is equal. And in this case, people already for 100 years know that there should be large parabolic magnetoresistance. In our case, because we have such, despite frequent Planckian scattering, mobilities are very high, about 50,000, which is really nothing else comparable at room temperature to graphene mobility. This magnetoresistance should be very high, and indeed we see parabolic magnetoresistance, which is at room temperature is 100%. People have been fascinated for 100 years to find materials which show large magnetoresistance for applications and for fundamental physics, and there is a lot of work, and sometimes people see a huge magnetoresistance, usually at liquid helium temperatures, sometimes at liquid nitrogen temperatures, but if you go to room temperature where all applications are important, it's much less than 1% typically. Even in graphite and even in 2 layers of graphene, and this is shown here, this is bilayer graphene, magnetoresistance is very small. So graphene, monolayer graphene, is unique in the sense it gives a very high magnetoresistance of the order of 100%. For example, if you compare with industry important giant magnetoresistance, we have 10 times larger magnetoresistance, and this is what we get at all temperatures above liquid nitrogen temperature. So I don't want to go into details, but one of those things, we wouldn't see this large magnetoresistance if it would be this Planckian scattering, because Planckian scattering decreases mobility by a factor of 3, which means it would decrease magnetic resistance by a factor of 10, and instead of 100%, we would have less than 10%. What is a subtle physics is that in zero magnetic field, electrons and holes move in opposite directions, so they scatter very frequently. But when you apply perpendicular magnetic field, you get kind of movements in which electrons and holes move in the same direction. They have opposite side, but electric field moves them in the same direction. So Planckian scattering falls out of all the equation, which allows us to see this giant magnetic resistance in low magnetic fields. So that's another effect which is new, which we have seen, and somehow over the last 20 years, people, including ourselves, overlooked it. Let me emphasize how important is monolayer graphene with this kind of spectrum relatively to its close brother, bilayer graphene, which have common parabolic spectrum. The curves looks more or less the same for mobility, but if you put them on the same scale, its mobility of monolayer graphene due to this diminishing mass at the neutrality point is very important. And despite frequent Planckian scattering in both systems, graphene is unique even among similar systems. The next step is to look what happens in high magnetic fields, and again we have had a surprise here. It's a very large magnetic resistance. It's no longer parabolic, but its linear magnetic resistance really beats everything what people have seen before. So linear magnetic resistance is kind of another fascinated stuff. Already for 100 years, linear magnetic resistance has to be something special about electronic properties, and there are many mechanisms about, I don't know, a dozen mechanisms, maybe 7, 8 mechanisms, which were proposed to explain linear magnetic resistance. Some of those confirmed, some of those just speculations, and those linear magnetic resistance behavior comes in many new materials which people try to understand. Our case is very well characterized system, so we can do better because we don't need to speculate on or use any approximation. We know everything about this spectrum, so this is our advantage to understand it. When we put in high magnetic field, what we see is no longer this spectrum. Magnetic field becomes quantizing somewhere above a few Tesla. We start seeing Landau levels. Instead of this spectra which I showed before, we get essentially Landau level now, which is occupied by electrons and holes simultaneously. So the physics of linear magnetic resistance becomes quite straightforward. You consider cyclotron orbits as quasi-particles. So we get the standard formula to explain in magnetic resistance, but then there is a number of carriers, a number of our quasi-particles, and as we increase magnetic field generates more and more quasi-particles at the neutrality points, pushing them together, and this 1 power, the number of the particle increases with magnetic field, and this compensates 1 power of magnetic field. So in this case, the mechanism of linear magnetic resistance is new, and it might be applied for other systems where people don't know how it works. Now, my last topic is something different. Again, we approach to zero magnetic field, but instead of increasing temperature and generating carriers here by temperature, we apply electric field and we generate carriers by nonlinearity, by applying magnetic field. So this is so-called Schwinger effect, which is known, for 70 years, but it's known in particle physics, and it's known only theoretically, because this kind of magnetic fields are impossible to generate even in particle accelerators and so on. Our advantage is that our quasi-particles do not have, like electrons, they do not have mass, they're massless, so we can generate electrons and holes, or electrons and quasi-positrons by just applying electric field. So let's try to see how it looks like, and indeed we see this Schwinger production, which was elusive effect for whatever 70 years. We can clearly see it there. We can describe all those curves and find how they look like. We can look a little bit more in detail, and this goes a little bit into details of the system, but of interest of of the community where I'm working is, and probably there is one moment which could be of interest for you. So instead of looking for the neutrality point where this kind of peak, and this is where we see this Schwinger effect, we put a finite concentration and measure IV characteristic, how electric field changes current. And what we can see here, this is a normal linear response, but then we increase electric field, we start generating, speed up our carriers in homogeneous distribution, and eventually we get to the regime where the drift velocity, how our particles all together move, exceeds speed of light for graphene. It's Fermi velocity 300 times less than real speed of light, but in terms of quasi-particle, it's super luminous regime. So what happens in this case, all the carriers here move in the direction of magnetic field. We completely take all the carriers which were initially here. They move in one direction, and then we start generating additional carriers, Schwinger effect, but by electric fields. So super Fermi drift velocity regime. So it's hard to observe experimentally in monolayer graphene, but there are other systems which are currently people studying. So they are called graphene superlattices, and in this case it's very easy to see this superluminous regime where you drift velocity exceeding the speed velocity. And the reason is in superlattices, Fermi velocities effectively becomes hundreds and thousand times less than in graphene per se. This kind of caused a lot of interest in the community because this kind of curves becomes in superlattices very popular. Some of you probably heard that twisted bilayers of graphene can become superconductors at lower temperature. People publish this kind of a curve saying, okay, this is near superconducting resistance, and this is critical current, and this is due to this characteristic, it's kind of superconducting transition. It has nothing to do with superconducting transition in some of the systems. Other systems are, of course, superconductors, and this is just superluminous regime where you exceed the Fermi velocity. There are a lot of interest in physics which is involved in this kind of non-linear regime. You can get all these kind of Kandinsky plots, which are very informative, but I'm not going to go into the details of those plots. could be too specialized. So I just want to point you how to give you an idea how interesting physics is here. So look at this red curve. This is, we are at some finite magnetic field and we measure Hall voltage. Hall voltage is positive, means that the carriers are holes and they move, say, in this direction. So you get a normal response. And then you apply high and high electric field, and at certain moment, what you see that instead of Hall voltage move in one direction, it switches its polarity. Like instead of electrons, you get, instead of holes, you get electrons. And it's exactly what is happening. And here, the Schwinger effect plays a role. So essentially, there are this kind of weird band structures where you get Van Hoff singularities, which means that you have really very heavy holes. And this is Hall effect due to very heavy holes. Here, you start generating electrons from nearby zone, and those electrons are highly mobile, so they are in minority, but they overwhelm the effect, Hall effect due to the holes. This kind of physics is involved in this kind of system. So essentially, I overviewed what it is there. So that's my summary. I'm well in my time, so that's what we have been doing for the last 3 years. At least part of my group's research is here, and we address by having this well-defined clean system, we address such phenomena like record breaking, magnetoresistance, linear magnetoresistance at 0 Landau level, and quite spectacular similarities due to Schwinger effect and superluminous Fermi velocity in graphene. With this one, I'll thank you for your attention and acknowledge my collaborators in this work. Thank you. You are late. Yeah, it was quite clear. That's what I expected. Okay. Next time, don't ask for. It's fine. Yeah.
I wanted to ask, you show HBN in the superlattices. You show HBN in the superlattices, but you don't tell us about HBN. You don't tell us why you're using that.
HBN, it's kind of called white graphene. It's a material which is also hexagonal structure, but instead of carbon you get boron and nitride, and this is the same, essentially hexagon. It has very close crystal lattice, but it's an insulator. So, and it's a very wide gap insulator. So what we do, because it's insulator, we encapsulate, we put graphene on top of this HBN and close it with another HBN layer. So it becomes like heterostructure. We called it van der Waals heterostructure, one of those many van der Waals heterostructures you can do. And the advantage is that HBN is not conductive, very, very kind of non-perturbative material, unless you align it exactly in the direction of graphene. In this case, you get a distortion of the crystal lattice, and you get additional periodicity. And this additional periodicity is called superlattice. And this is additional periodicity creates kind of yet another crystal with its own properties, and these properties are described by those band diagrams I have shown you before. They are called graphene superlattices, very popular subject for the last 10 years. It has brought a lot of attention and a lot of new results, including, I don't know what. Okay.
Okay. And I just wanted to ask about the origin of the inhomogeneities that you started out with, and how you got around that.
Inhomogeneity, it's a way of life. Whatever you cook, there will be always some impurities in your system. In our case, initially inhomogeneity was mostly due to extra charges in substrate. When using HBN as an insulating material, no one knows what it is exactly. Probably still charges in HBN itself, although the amount is minimalistic. Maybe it's strain, which is no one knows what's happening on this level. It requires further investigation, but this is how you improve your system. And people have said well before me, when you improve the quality of your system by 10 times, you always find a new effect, or probably several new effects. And I demonstrated a few of those effects we have found just improving the quality by a factor of 10. Okay.
There's a question here.
Very, very exciting results that you have shown. I have just one curiosity that how come these effects are so pronounced at such a small magnetic field? Because the field that you are exploring is something like 30 millimeters.
Yeah, that's the quality of the system. So this is how carriers behave. So what's happening? You apply magnetic field. In ideal system, instead of straight lines, electrons would move along electric field. They move like that. If you apply infinitely small magnetic field, then according to any theory, you should start getting this kind of circular trajectories which moved in spiral sideways. It doesn't happen in infinitely small magnetic field because there is a finite size of the trajectory, and scattering kills those. And essentially electrons don't know that they move along cyclogram trajectories. They just start in deviating a little bit, and then scattering occurs, and this destroys. The cleaner the system is, the more effect of your electric field, so there is time for carriers to react to the effect of magnetic field. As I told you, this is the racket system out of all those systems we know. So in terms of its cleanliness, and because it's the cleaner the system, the smaller magnetic field is required to see magnetoresistance effects.
Okay. Thank you.
I have another question. Sorry, Andrei. You talked about the negative mobility of the holes because of this drag effect. Is that also new physics? Because you've got a lot of new physics in here, and I wonder if that's also...
Yeah, so yes and no. The drag has been... people try to see the drag for the last, 40 years since I was a PhD student, and people did this kind of system where there is one layer of carriers and put very close another layer of carriers. So in gallium, aluminum arsenide, silicon and other structures, silicon, germanium, people reported the drag. It was not negative drag, it was kind of these carriers just push these carriers by Coulomb interaction. We also studied this in our group, was the first studied it in bilayer graphene system, one layer separated in another layer system, and then you see a strong drag. In our case, we get two type of carriers within the same plane. So it's ultimately strong drag effect, and negative mobility has not been seen before because the strength was not there, but drag has been seen before, but not negative mobility.
Okay. Any questions? Because I've got one more if there aren't any. Sorry. I mean, there's lots of beautiful physics, but you concluded that, you've got this really large magnetoresistance effect.
Yeah.
And it's better than what's out there, industry, So, but the reality is that you don't need to say that maybe because...
The reality is it would never be used in industry, in fact, because it's too complicated systems to make. So what it gives you an idea how you can improve or how can you find other systems. So actually one of my colleagues misunderstood this magnetoresistance in Manchester, so he tried to sell this as dealing with graphene himself. He tried to sell it to Seagate, and Seagate came and said, we want to have these sensors which are more sensitive than we are using to this one. They're so good, and without realizing that not only it's hard to make this system, but it won't work because they need sensors which are very small, and our sensors has to involve cyclotron trajectory, which is sub-micron size, not nanometer size. So it tells you, it builds up background for possible applications, probably in another system, but not directly given any direct applications.
Thank you. Right. All right, I think we've grilled him enough, so thank you very much for a wonderful talk again.